In this exercise, we're going to determine an integrated rate law for a reaction where any old reactant A becomes some product. In order to write down a rate law for this reaction, we can take one of two approaches. We can either think about the rate at which our reactant A disappears, or we can write down a rate law like we learned about in class. In the first manner, we describe the rate of disappearance using a negative sign because our reactant will be going away. And we describe the rate of disappearance as a differential, the change in the concentration of A over time. This is the rate. Another way to write this rate is to express it in terms of a rate constant, K, multiplied by the concentration of reactant A raised to some power that's, at this point, not determined. Notice that both of these relationships, equation 1 and equation 2, both give us rate. Rate is equal to negative change in concentration of A over time, or rate is equal to a rate constant K times the concentration of A raised to some power. Wouldn't it be useful if we could just set those things equal to each other? Let's do that. The change in concentration of A with respect to time is equal to a rate constant, K, multiplied by the concentration of A raised to some power. In order to solve this equation, we're going to take a series of cases where we assume a value for this exponent n. In a first case, we're going to think about the case where n is equal to 0. This is a 0th order rate law. So let's solve when n is equal to 0. If n is equal to 0, then we have the concentration of A raised to the 0 power. Anything raised to the 0 power is 1. We end up with an equation that looks like this. Negative change in concentration of A with respect to time is just equal to a rate constant, K. Rearranging this equation in order to get terms of A and terms of time on opposite sides of our equation, we can multiply both sides by dt and carry a negative sign over to the right-hand side. We end up with a differential equation that looks like this. We can solve this differential equation by integrating both sides. If we start our reaction at time 0, say, and allow it to go till some later time that we could just call time t, then our concentration will have changed from some initial concentration to some concentration that we have later on at time t. In other words, the bounds of our integrals will look like this. We'll integrate the left-hand side from concentration of A at time 0, our initial concentration, to our concentration of A at some later time, time t. On the other side of our equation, we'll integrate the right-hand side from time 0 to our new time t. Notice that our rate constant, K, is just that, a constant, so it's not affected by integration, and we can just pull that out in front of the integral. What we end up with on the left-hand side is the concentration of A integrated from A0, initial concentration, to A sub t, concentration at time t. On the right-hand side, we have a constant negative K out in front, multiplied by t, integrated from 0 to time t. From this, we end up with concentration of A at time t minus concentration of A initial, or at time 0, is equal to negative K times t minus 0. Rearranging one more time, and we end up with this. let's rewrite this equation in a slightly different way. Let's put concentration of A at time 0 on the other side of this equation to make it look a little bit more familiar. In General Chemistry 2, we like to make things look like a straight line. Notice that this equation looks like a straight line if the left-hand side is y. This whole quantity, k, with a negative sign out in front, is a slope. If time is like x, and if this quantity here, a at time 0, is a y-intercept, b. We know that the y-intercept and the slope define a straight line. We could sketch out a straight line for this integrated rate law, where along our vertical axis we have concentration of A at some time t, and along our horizontal axis we have time. We know that our y-intercept will be some initial concentration, and that initial concentration is greater than 0. Perhaps it's right about there. We know that our slope is negative because there's a negative sign out in front of our k. We know that this represents a straight line. Every 0th order reaction will have a graph of concentration of A as a function of time versus time be representative of a straight line with a slope equal to negative rate constant, k. If only we knew the slope of this straight line, we would be able to determine the rate constant for a reaction represented by this integrated rate law.